works on random graphs and random matrix theory.
Thank you. So, good morning, everybody. And there are several mistakes. The title was wrong, the abstract was wrong, and the affiliation was wrong. I have now much more complicated affiliation, but I am not going to. If anybody has questions, I'll explain in the question time. As a matter of fact, this talk is very appropriate to be given here because it is here 3 years ago when I was exposed the first time to the rich subject of discrete Laplacians on graphs. And I think some of the people who were here taught me the elementary concepts, and I was trying to absorb them in my way and to make some progress. And some of the progress is now covered by several papers by my students. Jonathan Elon, ex-student, he just finished. Idan Oren, who is still, and Amit Gudel, who was. And I am thankful for the Newton Institute and for the participants in the AGA for actually bringing me closer to this problem. So what I would like to do is to survey, in a way, what we were doing in the last 3 years, and at the same time, or simultaneously, bring up a few questions which might be of interest to people who are doing combinatorics on graphs, and some guesses, or some people call it hypotheses or conjectures, that might be of interest to people who are doing this work, this subject. So, in short, we are speaking about particular kind of graphs which are simple, so they don't have double edges or double loops or loops. I will call the number of vertices capital V, the number of edges capital E, and the key player in the game is the adjacency or connectivity matrix A, which for such graphs is 1 or 0, depending if the edge is connected or not. I'll assume also that degrees of all the vertices are constant, so we are dealing with D regular graphs. And one can prove that V times D must be even. There are many correlations which are more important than this correlation. The regular graphs appear in many, many applications, beginning in computer science and ending in number theory. And there are nice papers written about it. I'm not going to review it. Enough is to say that I'm calling the ensemble of all the D-regular graphs on capital V vertices G, this G, and then one can compute, estimate the number of such graphs when capital V goes to infinity, having D fixed, and it is going to infinity faster than exponential. So it's a huge family of graphs. And if you endow them with a uniform probability distribution, then you can do averages, and you ask all kinds of questions about the mean or the expectation value of some property for these graphs. And I'll denote this mean by rectangular brackets. If I remember, I put G. Maybe I forget. It stands, so the G is there. So what we would like to do is to study several properties of the Laplacian on such graphs, and which have to do either with the spectrum or with the eigenfunctions. And we'll start by the spectrum. And on the title, there was one word, keyword was random matrices. So I can go in one page through everything which one has to know about random matrices. And what we mean by random matrix theory or random matrix ensembles, let us consider only two examples. The first is the Gaussian orthonormal ensemble. These are the ensemble of n times n symmetric real normally distributed random matrices with this distribution function. So this is a Gaussian distribution and the function. And then the other one are the Gaussian unitary ensemble in which H are complex Hermitian matrices, and the distribution law is about the same. Now, a lot of work was done on these random matrices, and many questions were asked, and very few of them were actually solved, but there are many computed quantities. One of the computed quantities is a simple one, and that is you ask what is the expected value of the spectral density. So you take all the eigenvalues in the interval j for corresponding to j from 1 to capital N, and you average this quantity, and you ask what is the expected value. And then this was calculated first time by Wigner, who actually introduced many of these ideas and applications in particular, and you find that the spectrum is supported in a finite interval. And if you normalize the spectrum by square root of n, then you find that there is a constant interval out of which, in the limit capital N goes to infinity, there are no states. This is a very simple result. The next one, which has to do with spectral statistics, so you are asking the following question. Suppose that you take any successive intervals between successive eigenvalues, and you divide by the mean, by the expected value of this difference. You generate then a quantity Sn, which on average is equal, on average it has the value 1. And then you ask, what is the distribution of such nearest neighbor spacing on the ensemble? So you take a subsequence of k, of delta k members in this sequence. When you take the sum and you look at the average value, the expected value, and then Wigner gave very good approximations for these probabilities, nearest neighbor probability. For the GOE, it goes this way. For the GOE, it goes that way. It tells something about how eigenvalues repel each other in the vicinity when they are very near to each other. So this is linear, this is quadratic. All this is very well known, and this is more or less what I'll use from random matrix theory. But now let's go back to graphs and see how graphs start to fill into this picture. So I remind you, we're speaking about d-regular graphs. The Laplacian acts on a vector f in this way. The adjacency comes here as a matrix, and because d is constant, this number, this matrix is just a constant shift. We also remember this is just a minus, so we just look now, instead of the Laplacian, it is equivalent to look on the adjacency spectrum. So we shall, from now on, but for one example, only look at the eigenvalues of the adjacency matrix, and we ask again, what is the mean spectral density? Now, for d-regular graphs, Kesten and Mackay in the 80s actually found an explicit function. And this function is written in this way. If you do a quick calculation, you'll see that when d goes to infinity, this goes to the normalized semicircle, because the support here is 2 square root of d minus 1 plus minus, and on average, this is what happens when in the limit when capital V goes to infinity. If you don't believe them, you do a numerical test. Never believe a proof, a theorem. Always test it numerically. Then you find a very nice agreement. This was done by other people. I'll give the names in a minute. But you see, the distribution is supported only in a finite interval. There is nothing behind, and in the middle, it gives all the way between d equals 3 and d equals 6, but d equals 5, and it works. Believe me. Okay, it's a theorem.
Excuse me.
Yes.
How could one possibly know that the samples that one was selecting for this numerical data was uniform?
There are, you see, the field is extremely developed, and one knows how to generate sub-ensembles which are known to be uniformly distributed in probability in the ensemble. So if you average over a partial sum, then it converges to the exact sum because of the particular way that you build, you generate the numerical ensemble. If you're interested, there is a very interesting, good paper by Wormold, I think. It appears somewhere in the notes. I'll mention it.
So graphs are counted up to isomorphism.
Sorry?
Graphs are counted up to isomorphism.
Of course, yes, up to how do you call it? No. Relabeling of the indices. Yes.
Pardon?
They are up to relabeling of the indices. So now back to our business. This was kind of motivation that I also heard about it here 10 years earlier. There was a paper by Dmitry Yakovson, Miller, Rivin, and Zev Rudnik, who are number theorists, but at this time they were numerical experimentalists. What they did was to take such d-regular graphs, and they looked at the distribution of the nearest levels. But you remember that in order to look at the mean spacing, you have to normalize it by the average of the of the spacing. And the systematic way to do it, in this case or in any other case, is the following. We know the mean density. If we integrate it with respect to lambda, we know the mean spectral counting function. And you define a new variable, Sj, as the value of this function at the particular eigenvalue that you wish to look at. And because ds, just by taking this definition, ds is rho of lambda d lambda, and because rho is the local mean spacing to the -1, we have here d lambda over d lambda, and therefore the mean value of ds is equal to 1. So that is how we do what is called in the parlance unfolding. And in order to, after you have done the unfolding, and you remember this is quite important because the density here is not uniform. You have here there is a smaller density, here is another higher density. So you have to really to do the unfolding in order to be able to compare to the predictions of random matrix theory. They did it, and they got this nice fit, and they made a check, Smirnov-Kolmogorov test. That statistically, it is agreeing with the prediction of the theory, and that was the first indication that I know of. Maybe Audrey knows earlier indications that random matrix theory actually recovers what one sees on d-regular graphs for very large graphs. Well, you can even check it further by looking at what we call a magnetic adjacency matrix, in which you decorate every element of the adjacency matrix with a phase. And if you are careful to take phi ji equals to minus phi ij, the matrix becomes Hermitian. And then you can compare these results to the GUE statistics, which corresponds, as you remember, to Hermitian random matrix theory. And then this is the numerical experiment, and you see that it works perfectly well. Another check, which introduces another function into the game. Here what we do is to take the spectrum and map it onto the circle. So we take the number, divide by the total number, and I write here v-1, I forgot to say, because always there is a trivial eigenvalue. It is 0 for the adjacency, d for the adjacency, or 0 for the other one. So it is a trivial one, so we exclude it from the game. And you look at this distribution. This is a two-point distribution function because it takes all the possible pairs between eigenvalues now mapped on the circle, uniformly distributed on the circle. And then there is a specific prediction for this function from random matrix theory. First of all, it tells us that even though there are two parameters here, t and capital V, which a priori are completely independent, the result is not, because the result depends on the ratio between t and v. We call it tau. And then, if you plot this function as a function of tau, you get this numerical data for the GUE and for the GOE, and the red line is the expectation from random matrix theory. Another test, and the advantage of this function is that it's the simplest non-trivial statistics that you can compute. And we shall use this function again and again. This is called the form factor. It is the Fourier transform of the two-point correlation function in the spectrum. And remember, we have to do the unfolding. We had to take the spectrum, which is not uniform, and to uniformize it after putting it on the circle, or at the same time as putting it on the circle. Okay. And the question to be asked is, why does it happen? Why suddenly d-regular graphs behave as if they were a standard chaotic system? This is quantum chaos after all. But where is quantum chaos here? And what I would like to show to you that from what we know about the statistic of cycles on these d-regular graphs, and by using a trace formula or trace formulae, which are coming into this game, we can relate this spectral statistics to the statistics of counting on graphs, counting these cycles on graphs. The cycles, however, are very particular. They are the ones in which you never go back as you advance. I call it NB, non-backscattering. It should be called non-trace, not self-tracing, or there are other names to it in the literature. But let us call it NB because all my slides have this NB, so no backscattering. This is quite strange to somebody who comes from quantum chaos or quantum graphs, because there you have to take all the possible ways. Here you are not going backwards. You can go backwards after you went forward. I mean, you can repeat an edge which you went forward at some stage, but you cannot scatter backwards at the one go. So the red thing is forbidden. What shall we use in all this discussion are some known results about d-regular graphs, and there are many of them, which I just put very few nutshell information. So if you take the R neighborhood of every vertex, and R is less than the d-1 logarithm of V over 2, whenever I write log, it will be with respect to this basis. Is almost surely a d-regular tree. So in the vicinity of every point on a vertex, when you look not far away, you see a tree with high probability. And then a quantity which will be also very important is the actual counting, the number of T cycles, so primitive, non-backscatter, non-self-intersecting T periodic orbits on the graph. And then there is a established theory which tell you what is the statistics of these numbers of CT. And from the work of Wormold and others, and Mackay and Bolobas, you know that these CT are distributed as independent Poissonian variables, and the average of CT on the graph is d-1 to the t over 2t. And that you can prove, you can think of it quite easily, because you can ask what is the probability to make a cycle of a length t. Then you choose the first one, capital V times, and then you go to any other. You have d choices, so multiply by d. The next one, you are not allowed to go backward. So you multiply by d-1, and you multiply by d-1 again, and you gain a factor of d-1 to the t-1, because at the end you have to come back to where you started. So the final edge has to be a very particular edge. And if you count, and this I leave you as an exercise, what is the number of such restricted edges, you get a result which is this. This is quite surprising. You see, but it tells you, for example, that the number of triangles on a d equals 3 regular graph is 2 to the 3, which is 8 divided by 6, so it's 1.5. So the average number of triangles on a million vertex d regular graph is 1.5. or you take trillion, it's be the same number. Okay? And this is a correct result. I didn't say that all the graphs don't have more. There are many other graphs which have many triangles, but they are distributed in a certain, yes?
The independent variables,
Are the counts.
I understand the independent.
The average is over the ensemble G, in which you give uniform probability to every graph.
So CT is independent for CT.
T is the cycle, the length of the cycle.
Yeah. So CT is
And
independent from CQ.
T1 is not dependent on T2, and you divide it by 2T and not by T because they are usually counting both time reversed and in the same time. I mean, they do not distinguish between time reversed. Okay, so how do we make the connection? And the connection goes to a formula which is called bus identity or Bertoldi's identity. I learned all this from Harold, I think, Kaufman, in your lectures 3 years ago, or similar things. And then what you see here is an identity between two determinants with some factor. This determinant, if you consider this just as a number, x, then you can see that this is the characteristic polynomial of the adjacency matrix. So if you want to know the spectrum, you want to know the traces of this. So this determinant gives you the characteristic polynomial. Solve it and you know the spectrum.
I think left-hand side gives Ihara zeta function.
Right. It is just coming. And the matrix which appears here has the dimensionality of the number of vertices. Up to a factor, it is equal to another determinant. This time, the matrices which appear are of the number of directed bonds, 2e. E is the number of edges, 2e is the number of directed. And it is an operator y which is composed in the following way. First of all, b is nothing else than equal to 1 if the terminus of the first edge is equal to the origin of the second edge. So it is a connectivity in the language of directed edges. And then you subtract out of it that matrix which connects backward going edges. So y, which appears in the bus formula, is equal to b minus j. And you can immediately convince yourself that the number of t-periodic walks is trace of b to the t, or trace a to the t, because a trace will just count how many times you can go from a vertex to itself, walks, not periodic orbits. And the number of t-periodic orbits without backscattering, the ones in which this is eliminated, so it is y, is trace y to the t. And what you see here is that there is a very nice connection between y and a. So the natural connection is not by something which counts all orbits, but by something which counts only non-backscatter orbits.
I have just one comment about this bus identity. You are talking about in the case of the regular graphs.
Sorry?
You are treating the regular graphs.
Yes?
And in the case of the regular graphs, this identity is essentially due to Ihara himself.
Okay, so then you are, first of all, you are my teacher. So what I know is from you, and you are right.
Anyway,
And
Bas gave general.
Bas generalized it, and usually I have here the Bartholdi is generalized by putting here a little omega, and so I made I did cut and paste from the wrong place. And this is this morning's work. So what we can say is that the spectrum of A can be used to count the periodic walks, because if we know this, we know this. And vice versa. If we know this, we know this. So it is this dual relationship which is very important, and this is where ideas from quantum chaos come, or from number theory come, because in the Riemann zeta function there is the duality between the primes and the zeros on the critical line. In quantum chaos there is a duality between the spectrum of the Hamiltonian, of the quantized Hamiltonian and periodic orbits. So it sounds more or less the same. Okay, if you work it out, suppose that you know the spectrum of the the spectrum of the adjacency matrix lambda L, then you immediately see that the spectrum of the operator Y is, apart from some trivial part, is completely given by solving this quadratic equation. Lambda L is known, so the corresponding eta is the result of this solution. Now, let us assume that the deregular graph that we are dealing with, or the part of the spectrum which we are dealing with, is within the Ramanujan, so it is within the support of the Kesten-Mackay distribution. Then we can look at the phases phi L, which are defined as the lambda L divided by the size of the support. And this is, these are real phases, and therefore the etas can be written in this way. And if you can, now you know the spectrum, you can write a trace of y to the t. You remember trace of y to the t is the total number of counts, which of walks which went t times of length t. And then you see that there is some average number. There is some number which fluctuates. When t is odd, this is 0. Even, it is e minus v. It's a large number. And then there is also a part which looks fluctuating with t. And this is the part which comes because of the idiosyncrasies of the spectrum. You change the spectrum of A, you change the number of counts. This is independent of the spectrum. And if you remember that phi is r cosinus, and you remember that cosinus of n r cosinus of x is the Chebyshev polynomial of second class, then you get this result. So the trace is given in terms of the spectrum. You work a little bit and you get a trace formula. The density is equal to Kesten-Mackay density plus a fluctuating sum, which is very much in the same spirit as all the trace formula that we know and love. You count periodic orbits. All of the periodic orbits or periodic walks of length t are put here, and the yt is the number of t periodic non-B walks, walk, minus their average, divided by some constant. And this is just a fluctuating phase. You can write it also in terms of the t of the Chebyshev polynomials. And what we get out of this for free is that since we know that the average of yt is equal to 0 for t sufficiently small, and this is Wormald, Mackay, and Bolobas, because this is the average. And then when we go to capital V to infinity, we found that this average is 0, and we gain the Kesten-Mackay result. The original way of proof of Kesten-Mackay was completely different. What they did was to study periodic orbits on the tree. All the distribution of the periodic orbit of the tree comes here. And this contains all those which do not have the tree property, because here there is no backscatter. On a tree, since there are no loops, you have only periodic orbits which must backscatter. So there is a very nice dichotomy between those which do not and backscatter and those which do. And then, forget about the problematics. You can then do spectral statistics. You look at the fluctuating part, which is the density minus its mean. You have this form. You do some exercises with the Chebyshev polynomials. You get that this normalized counting is equal to some Chebyshev transform of the spectrum. If you take y squared and average over the ensemble, you find, just from here, that it corresponds to some transform of a two-point correlation function. This is spectral statistic. this is counting statistic. This is the variance of the counting of t walks. And this is spectral statistics. And if you go to the variables, or the angular variables, you find it in this way. You have to remember, however, that this average this function is taken with respect to the original angles which were not unfolded. You remember, in order to compare to random matrix theory, I have to take the phases on the circle and distribute them uniformly. This corresponds to the distribution of the Mackay-Keston formula. But nevertheless, it's a nice result. So we can sum it up by giving this function a name. Phi k is the spectrum not unfolded on the circle. This is k tilde is the not unfolded form factor of the two-point correlation function, not unfolded, not unfolded, not unfolded. And what we find is that there is a very nice correspondence. The variance is equal to this spectral form factor with the unfolded spectrum. So from this spectral information, you can get information about the counting. Now, you can now go further and ask what is known about these numbers. Well, I told you before that one knows that the CT, the number of T periodic non-B cycles behave like Poissonian variables. If you remember the definition of this little yt, it was this trace of yt minus its average. So k of t in the limit when t is constant and capital V goes to infinity, by this Poissonian distribution tells you that the k of t is equal to a factor times the variance over the mean. But in a Poisson distribution, the variance is equal to the mean. And therefore, this just gives you t over v is equal to tau. Now, there is another thing which you can ask, what is the relationship between k tilde, the form factor of the unfolded spectrum, and the form factor of the folded spectrum in the same ensemble? And you can, this I shall show you in a minute, but then in this particular limit, when tau goes to 0, you can show that the two of them are the same up to a factor of 2, and therefore the unfolded spectrum of the graph, unfolded form factor of the graph, in the limit tau goes to 0, behaves like 2 tau, and this is exactly what you get from random matrix theory. And this is very similar to the very old and important result of Michael Berry, in which it is called the diagonal approximation, which also assumes independence of actions, of periodic of actions. And this independence is expressed here as the Poissonianity, independent Poissonianity of these numbers. Well, if random matrix is so nice, let us make the comparison even further. So we were able to prove this slope, but now we can derive an identity which tells you if you know the unfolded spectrum, the form factor for the unfolded spectrum, the folded one will be, the unfolded will be this. And so you can compute the corresponding result numerically for k tilde, and you can compute, you can take for k either the COE result, if you don't have magnetic phases, or the GUE should be here for the magnetic, and then you see that there is a perfect agreement using this formula. So it means that not only what we know about periodic counts from combinatorics theory holds, but also a lot of things which we don't know. And therefore, I would like to pose a conjecture. And this conjecture goes very much in the spirit of John Keating's and Snipe hypothesis, which allow them to compute moments of the Riemann zeta function based on the assumption that the Riemann zeros are behave like random matrix theory. What I'll say here is the following. I'll use this relationship. And I know now that I can express this variance, normalized variance, which is a purely combinatorial issue. I can express it in terms of certain form factor, spectral form factor, which I'll assume to be GOE. And then we know this function of GOE because we know it is written down explicitly. Here it is written down. You see, K is equal to this function. This we know from Kestel-Mackay. So this is a function of tau for any P and V such that T goes to infinity, V goes to infinity, and tau is constant. And we claim that this function gives you the entire information. So random matrix theory, now I claim, gives you the information which you don't know from combinatorics. And I showed you the fit, how nice it works if you look at it one way, but you can also look at it another way. And what you see here is exactly the expression for d equals 5, d equals 20, and d equals 10 here is a lonely planet here because there was no place to put it in between. But you see that it works very nicely. And you can also compute asymptotically this expression, for example, for small tau, and get not only the leading term, 1, which comes from Poissonianity, but also the correction. And to our amazement, the correction is of order square root of tau. I don't know why. I really don't know why. Another result, which you can also derive very easily, is we know that K goes to 1 when tau goes to infinity. This is due to a very deep result, also conjecture if you wish, that the spectra of d-regular graphs are not systematically degenerate. There is no systematic degeneracy in this spectrum. And this simple fact tells you that the variance of C divided by its mean times tau in the limit tau goes to infinity goes to 1. So it means that this going out like 1 over tau. Now you should remember that what we are dealing here with is the T is larger than V. So the time, the period, is much larger than the available number of vertices. So we go over many vertices many times. And even this result, to the best of my knowledge, is not known. Is Adam here? Where is Adam? He didn't come. So I gave this as a problem to a student because he didn't have what to do. So maybe he solved it since I saw him last time. But if anybody of you knows this simple looking result, please let me know. I will be very happy to know about it, but combinatorically. Okay, so I posed one conjecture, and now I'd like to pose the second one. Okay, I don't have to speak about this, so I think I'll erase it. And another concept I would like to speak about, and this concept relates to eigenfunctions or eigenvectors. The concept of a random wave or random field is quite general. If you have functions over some manifold, then you can define a Gaussian random variable, psi of x at each point, and it is completely defined in terms of a covariance, which you decide will be the covariance. Random waves, which are usually used, and these are the solutions also of the wave equation, are the monochromatic waves in R2, and then the corresponding, the correct covariance is the Bessel function. If you take random waves on the sphere, so you take spherical harmonics with a fixed L, and you give them random independent Gaussian coefficients, you get another covariance, which is the Legendre polynomial, and here x and y are the two angles, 2 points on the sphere. Now, Michael Berry in 1977 proposed the following conjecture, that the statistics of eigenfunctions of chaotic billiards in the semi-classical limit are reproduced by the Gaussian statistics of random waves. So you take Gaussian random waves with this covariance, you compute certain averages of some operators, and lo and behold, when you do it numerically, as long as the domain is chaotic, they reproduce each other. There is no proof, but it works. So let us see what happens if you want to copy this kind of ideology into the language of the graphs. And the first thing which you would like to know is what are the random waves. And this is a work which was done by Jonathan alone in his PhD thesis, and I am not an author of this article, so all due to him. So if you take the tree, let us start with the tree. This f of lambda is the eigenvector corresponding to the eigenvalue lambda on the tree. And you can compute this quantity, which is the probability, this is the sum over all the vectors which, all the quantities, all the amplitudes fj of lambda, which are a distance k apart from I, multiplied by fi, so this is a correlation function, divided by the number of them and the mean value of at the beginning. You can show that on the tree there is a recursion relationship which controls this quantity as a function of k, and this recursion relationship is solved by a combination of Chebyshev polynomials, this time of the first kind. It's well known. And what Jonathan have shown as a part of his thesis was that Gaussian random vectors on the vertices of an infinite d-regular tree with covariance this one are almost surely eigenvectors of the infinite tree graph with this eigenvalue. Now, you remember that in the covariance which I showed you on the plane, on R2, the wave number k, the eigenvalue, or the square root of the eigenvalue, was scaling the distance. Here the scaling doesn't exist. This is much more complicated function of lambda, n of d. Okay, and what is the conjecture? The conjecture is that random wave, that the wave functions behave statistically as do the wave functions on the tree, but for d-regular graphs in the domain k smaller than log v. So this is a conjecture, not proved. And what I would like to show you is that conjecture is very fruitful, and therefore it is even maybe correct, and therefore it calls you for proofs, if you can. So first of all, the question is whether or not the wave function, if you take a typical wave function or typical wave function, and they really distribute as random Gaussian variables, not on the tree, but on the d-regular graphs. I don't have the numerical checks. He did the checks, they work. The second question is compute the covariance out of as a function of lambda of the wavelength, and this is for k equals 4, k equals 6, and k equals 5 and 6. K is the distance as a function of lambda, and you see as long as k is equal to 4, 5, and 6 for a graph with 4,000 vertices of order d equals 3, the fit is very good. But it completely, it starts to deviate when you go to k equals 11, k equals 12, and that is about where the log of capital V over 2 starts to be equal to d minus 1. So that's the reason. So we expect it to happen. But the numerics works, so this is another indication that something may be correct. But let's now look at two results which follow from this assumption. The first result is about nodal domains, and I don't want to go into all this theorem, but you know nodal domains on the graph are subgraphs on which the wave function have the same sign, so the maximally connected ones, and you can count them, and then you have the numbers, and the current theorem also holds that the nth eigenvalue has at most n nodal domains. And let us now look what happens on graphs. on D regular graphs. And this result actually was first discovered by a number theorist in Jerusalem, sorry, not a computer scientist in Jerusalem, and they could not explain it. And what you see here, and here I speak about, here the J is the index of the Laplacian eigenvalues, not the adjacency, because with the courant we always compare with the Laplacian. So instead of changing this line, we change this line. And now the courant bound tells you that the number of nodal domains is equal to the index of the level, and you see that the behavior here is very strange. The number of nodal domains is almost 2, around 2, 3, or something like that, very small, and then it jumps up in a very particular way, depending on the parameter D. Now, Jonathan alone was able to reproduce these lines using this assumption of the random wave conjecture. And the simple argument, or the leading argument, goes as follows. If you consider an eigenvector corresponding to the eigenvalue lambda, after all, what you do is to delete t edges where the sign is different on the two vertices which define this edge. So what you get now is a graph which is not connected. It has many components. And the number of the edges on this graph is e minus t. Now, if you can compute the expected value of t, you can compute the expected number of edges on this graph. We know that the general result, in which you don't have one graph, connected graph, but C component graph, there is this identity. And if, when R is the number of cycles in the components, the cycles in the new graph, in the components which remained after we removed, cut the edges. Now this number is, if you neglect this number, then you have an estimate of the number of components because you know capital V, you know E, E is just E minus T, T you computed because you can always use the random wave approximation and the correlation function to get this average. And the average will depend on lambda and on D as given by this covariance function. And Jonathan performed the calculation, and lo and behold, this is the numerics and this is the line. And then if you take D equals 6, he can get even better approximations. This is the original one, this is the simple one. When you get further approximations, you can really approach the numerical value, which is, I think, is a very impressive result for those of you who are impressed by nodal domains, but it is very strong also result because it tells you that very detailed quantity, depending on both lambda and D, can be reproduced to a high accuracy using this only assumption of the conjecture. Another property of random graphs which was studied in other contexts is percolation. If you take a graph, a complete graph, and you retain a bond with probability p and delete a bond with probability 1 minus p, you see that there is a phase transition, and the phase transition separates between having one large component, so one macroscopic component, and not having it. And the transition and the probability is 1 over d minus 1. 1 over d minus 1 is very, very natural because this is, you remember, this is the number of times you can go out. So you want to have, if you want to have a large component, and if the level is larger than 1 over d minus 1, then always you can find one bond to which you can continue to the next one, because the probability is 1 over d, or 1 over d minus 1, if you don't want to remain in the same place. So this is a natural result, and this is the result for percolation theory, and therefore, if we see percolation, if you want to look at percolation on graphs, we cannot look at nodal domains, because nodal domains correspond to equi-probability of positives and negatives. And therefore, we have to look at something else. And what we look at are level sets. So you have a graph G, and you have a vector F, and you take the subgraph, which is equal all the vertices in G for which Fi is larger than alpha. So this is like you have the graph, you fill the bath with water, and you look which vertices have a function which is higher than the water level. So in order to look at this numerically, if there is a transition, you look at the largest component, you divide by the entire graph G alpha, and you look how this behaves as a function of alpha for various values of lambda. So these are various values of lambda. This is due to statistics, don't worry. And then you see that there is a transition from 1 to 0, and the transition is quite fast. Of course there will be a transition, because if you start from below, everybody is up. If you are above, everybody is down, so there is a transition. The question is whether this transition is discontinuous, fast. Now, discontinuity you cannot determine with 1,000, 4,000 vertices, but you can check how discontinuity becomes better, or how the jump becomes more steep as you increase the number of vertices. And I think I don't have here the picture, but it does become larger. Okay, so the question, can you explain this phenomenon? And can you also find a function, an explanation for the critical alpha where the transition occurs? So suppose that you define the critical transition at the point where the slope is maximal, so here and here and here, and then you'll have alpha critical, which will be a function of lambda, and which will be a function of d. So two-parameter function. So the numerics is given by the various dots, and the lines are the theory. And the theory is based only on the assumption that you have the random wave conjecture works. Another independent test of the same assumption, and it is quite fertile. Now, what Jonathan was able to do was to show that if you make the same test on the infinite tree, then there is a transition. And this he proved, that there is a transition. And the transition there for the tree is exactly what the function which describes the transition is the function that you are seeing here. These are the functions we have calculated for the tree. But because the d-regular graph is locally like a tree, then if all the localities are percolating, then you have a good chance that it will percolate all over the place. And this is the explanation, not the proof, why it works. But always it is the locality, the local behavior of the tree, of the d-regular graph as a tree, extending it and hoping for the best, and it so happened that the best actually works. So I would like to end here, because still I have 5 minutes, because maybe there will be questions, but I would like to make a short list of problems. So I challenge the combinatorial graph theorists. Please look at the counting statistics for NB-T periodic cycles, and please be able at least to have the first correction over the Poissonian distribution about which you proved 20 years ago. And then also, maybe you can also calculate why this covariance goes down to 1 over tau. It's interesting. The second is, can anybody prove the limits of applicability of the random wave conjecture in any sense? Okay, this is something which I think will end this lecture, but one can also ask similar questions about the VP ensemble. VP ensemble is the ensemble in which, as I told you before, you cut edges with probability P. So this is a more general ensemble than the one that we dealt with. It is more probabilistic, but here it is the graphs which are emerging are not d-regular. They're on the average d-regular. And what remains out of this discussion for this problem, I don't know. There are also very nice, interesting questions about isospectral graphs and about nodal counts. And one of the questions that we are always deal with is, can nodal counts distinguish between isospectral graphs? We have some results, some contradictions, but we don't have systematic view. And this is another interesting problem. And this is a problem where there is very rich results because there are many constructions possible to construct isospectral graphs. One class, very important, goes under the name Sonada graphs. These are the ones which Rami spoke about in the context of discrete graphs. They are following a symmetry of some global structure. But there are non-Sonada graphs. And this is another important family. I don't know how many names are associated to the non. It is not NON, not a number of names. But still, there is a very large richness, and it calls for further study. And with this, I think I can stop. So thank you very much.
Yeah, so all you talked about is deregular graphs, and so two questions in one. So first, if my random matrix sort of comes as the adjacency matrix of a deregular graph, can I see that in the, is that a property of the random matrix in some way that can be interpreted?
You see, first of all, the matrices are very strongly intercorrelated. You cannot just throw in D ones and the rest zeros. This will not correspond to a graph. You have to get that the connectivity should be right, and therefore this is not the randomness is not very simple. So the construction of in other words, the construction of the ensemble contains a lot of elimination of various choices. Now, another thing which I did not say, but your question points to it, is the following. If you take random walk on a deregular graph, it has the property that it covers the space exponentially fast. So it gets to the uniform distribution exponentially fast. And the exponent corresponds to the distance between the leading eigenvalue, the trivial one, and the first eigenvalue. And this is maximal. So it is fastest as can. So the graph is mixing, if you wish. So the classical dynamic is mixing. And therefore, you have the expectation, at least from the ideological point of view, that it looks something like quantum chaos. But this is all ideological.
Yeah, and then would it be possible to generalize that to some bigger classes of graphs that just have...
This is one of the questions which I'm asking.
Yeah.
What about the ergodicity of these results? If you take one graph out of your ensemble,
Yes.
would the mean be typical or not?
Yeah, so then for correlation it's typical. You know that usually it's very difficult to speak about the form factor because it is not self-averaging, so you have to average.
Your last graph, you said that the curve corresponds to the tree result,
Yes?
and the graph was size of the component. Why is component on the graph large or small?
You see, the statement is the following. Every deregular graph looks like a tree if you look sufficiently close.
Yeah.
The results are correct in the limit capital V goes to infinity. And then what you hope is that when capital V goes to infinity, you have a macroscopic part which is tree-like, and therefore we hope that it works. And then you have several macroscopic coverings or balls.
Can you show
Which picture?
the last? Yes. So the curve is
The
corresponds to the
curve
graph.
corresponds to the curve corresponds to a tree, and the dots corresponds to deregular graphs.
But on the tree, the connected component should be smaller because on the graph you have extra connections that can connect other components.
Maybe it should, but it doesn't know that it should. And the calculation shows this, so...
Well, maybe calculation is wrong. I mean, a tree is easier to
You
break
want to say
apart
that a
than a graph.
PhD from the Weizmann Institute does wrong things? No, I think it's
Asking
yeah,
asking
we
questions.
should talk about it.
You mentioned these non-Sunada graphs.
Yes.
What kind of symmetries, if any, do they?
I don't think it is symmetry related. As a matter of fact, there is a Bob, what was it? Bob, the one, Richard, what was his name? From the Technion who died 10 years ago. Bob, okay, yeah, Bob. He have shown that several of the non-Sunada graphs are really non-Sunada. So
So what is the key?
I don't remember. I have the reference, I can show you. There is also a very nice paper by Mackay, where he is not using all the properties of the graph. He just takes a subgraph, he does something to it, and then you get another graph which is isospectral. So it is not a global symmetry. This I have with me, I can show you. Good.
Okay, if there are no more questions, let's thank the speaker again.